Hello, I've been putting something together for a school, the local school to us, just to help them out a bit with their PA system. And one of the problems they've had with it is quite bulky, and moving it around if they want to do sports day or something, it's quite a big lump of kit to move around. And also it's separate, so there's a kind of console and there's also a separate amplifier. And the amplifiers are really big, heavy, quite old, maybe 10 or 12-year-old amplifier. And what I thought I'd do, and it's kind of had its time. It's got scratchy controls and so on. It's just a very old amplifier. So what I thought I'd do was just replace that. And I've bought this amplifier here, which is actually about a third of the size, certainly less than a third of the weight, and it's a Class D amplifier. And what I thought I'd do before that goes is do a quick teardown and have a look. And in order to explain what a Class D amplifier is, I wanted to spend just a few minutes and talk about how Class D amplifier works and how it looks different to a much more typical Class AB amplifier. So we'll spend a couple of minutes and just look at the theory of a Class AB amplifier and then a Class D amplifier just before we take it apart. And after looking at the basic architecture of the Class D amplifier, we can see if we can map that to what we find inside. Okay then, so conventional Class AB amplifier. So very simply, a Class AB amplifier is a linear amplifier, and what that means is the input signal is amplified, pre-amplified at least, and then driven into some output devices which drive the speaker. Quite easy. The signal you get out here is a lot bigger, and there's a lot more power than the signal going in here. And the power devices, in fact all the devices in this setup work in their linear mode. So when the positive half of the cycle here is being driven on the output, it's actually coming from this transistor here. And when the negative half cycle is being driven, it's actually being driven from this transistor here. So now when the really bad drawing, so sorry about that. When this transistor is switching, or these transistors are switching, they're switching in a linear fashion, and so what that means is there's the more output is required, the more drive goes in. This turns on harder and drives the output into the load up. Now, transistors and FETs are not particularly linear devices, so in this kind of amplifier it's absolutely mandatory when you're using solid state components at least, that you've got this negative feedback, and this negative feedback effectively linearizes the circuit to make sure that these transistors are operated in their linear regions. So that's the basic architecture, very simple, proven, well known. One of the issues with the amplifiers, in higher power amplifiers, these generate a lot of heat because the device or devices, if they're parallel, that are delivering the output power, if this is say 500 watts, then it's quite feasible to be delivering an equivalent amount of power, i.e. about 500 watts or a little less into these devices, and therefore in heat. So they're pretty inefficient, is the issue with them. And Class AB are probably the most commonly used because although they're inefficient, they can be made to be very, very good in terms of performance from a distortion point of view. So then, if that's Class AB, and if you look at this amplifier, in say a 500 watt variant, it's a really big, heavy piece of equipment. Normally got a pretty big mains transformer. Sometimes nowadays they've got a switch mode power supply, but big heat sinks, big thermal management, and all that kind of stuff is in there. Now, Class D amplifiers, like this one sitting behind me here, sitting here. This is 1,000 watts in a 1U case. It weighs a couple of kilos, or a kilo and a half. Very lightweight, very small. So how do we achieve that? So a Class D amplifier, although at a glance it almost looks identical, you've got front end amp, you've got output devices, you've got a load. Actually, it's a very, very different mode of operation, and I'll talk about that now. So you've got the front end amplifier. I've not drawn this very well, but with negative feedback, and actually in Class D that's optional, and I'll come back to that in a second. However, I'm going to stop here. I'm going to start at this end and talk about what happens at this end, because in a Class D amplifier, the output devices are actually switches. So this is very comparable to if you would have seen one of my earlier videos on the power supply that I'm working on. You know, you've got a PWM, so you've got a PWM signal, which is a square wave signal, turning each device hard on or hard off. So you've got a square wave signal. And then by varying the pulse width of the on time versus off time, will vary the average voltage at this point. Now, by default, with no input signal, you're looking for a 50% mark space ratio. So it's half the time it's on positive and half the time it's on negative. So in this square wave here, which is what you'll see at this point, although it's for half the time it's full output, full power out, for the other half of the time it's full power out in the other direction, the average voltage, of course, is 0. And that's the principle by which the Class D amplifier works, because what happens is this square wave is run at a very, very high frequency relative to the audio. Let's say, for example, 500 kilohertz. And it can run a lot higher than that, but typically 500 kilohertz to a megahertz maybe is where they'll be, and sometimes as low as 100 kilohertz or 200 kilohertz. And so that square wave is driven into a low pass filter. Now, I've drawn this in very rudimentary. There's normally a little bit more sophisticated than this because of the amount of noise. The problem you've got here is that this might be at plus or minus 50 volts. This is designed to be high power. This is designed to deliver, say, I don't know, 500 watts or 600 watts. And so suppressing all of that high frequency is really, really important, because if you take that away, what you end up with is a long wave transmitter. And that's, clearly you don't want something like that floating around in your PA setup. So this filtering is actually, normally a big part of these amplifiers. Is normally big inductors, big capacitors, lots of snubber networks, and a whole bunch of special tuning around that. But the principle is exactly that, as I've described. So you've got a full power output here at the switching frequency, going into a low pass filter, which will filter that out. So what you'll see here is an average voltage of 0. So you'll see no output. Now, as you vary, as the audio signal that comes in drives drives the input of this comparator, it's biased as such that when there's no input, this is sitting at the midway point, and the other input of the comparator is driven simply by a sawtooth, so a ramp generator. And the resultant output is a square wave 50% duty cycle, and as you drive audio signal into that, it effectively moves the cutover point of the comparator, and therefore creating a variable mark space ratio, so a variable mark space on this signal. And that varying mark space running at the audio frequencies, of course, makes it through this filter, so it lands up out here. Now, why Class D? What's the advantage? Well, the big advantage is you can achieve really high power output with actually very little loss. So these are very, very efficient in terms of power transfer. Could be up to 80, 90%, even maybe 95% possibly, but certainly up there. And the reason for that is quite simply, these FETs, these output FETs, are switches. They don't work in their linear region. So they're either on, and when they're on, if they've got a low RDS on, so low on resistance, because the resistance is so low, regardless of the, quite high current can flow here without dissipating too much power in this device. And of course, when the device is off, it's off, so no power is dissipated. So the only heat really that's generated here is during this transition period. So going from off to on. If you were to expand this out on a fast enough scope at whatever speed, you'll actually see that this isn't exactly perfectly square. It's slightly slanted like that. So that's where the power is dissipated. But typically, the reason why this amplifier here behind here is so small, and the heat sinks inside I wouldn't expect to be too big. Well, they'll be reasonable, but they certainly won't be anything like you'd see in a linear amplifier. Is it just doesn't generate enough heat to to cause a problem. So that's the basic setup, the basic principle. It's actually really simple. So the advantages, as I said, high power, really high power, portable, high density. You know, if you're putting big, huge PA systems in place, you know, where you maybe need 20, 30, 40 amplifiers, it's a lot easier handling these. You know, if you're mobile, if you've got mobile PAs, if you're a band and so on, you know, these things are much better. There are some disadvantages to them. So first of all, they're not particularly, they don't have a particularly wide dynamic range, and it's maybe hard to, I'm not sure I've got the skills to explain exactly why technically that is, but basically if this is, let's say this is a 500 watt amplifier and you decide to play it at 5 or 6 watts because you're just testing it, say at home in a room, or 10 watts. What tends to happen with Class D amplifiers is the top end, you know, in terms of sonic performance, the top end tends to roll off. They tend to sound a little bit undefined. And only when you get the amplifier working at sort of 50, 60, 70% of its power capability does that problem go away, and that's mostly due to the filtering here, because you know, you can't make a perfect low pass filter. It's got to roll off, and you know, you've got to pick that very carefully. And even at you know, 10 kilohertz, if you've got you know, high frequency transitions that are quite vertical, then this filter is going to have an effect, and that effect is considerably more when the signals are small. Relative to the levels that the filter's been designed to work at. So that's one problem. The second problem is the filter itself introduces distortion. So if you want really good quality audio, you typically don't see Class D amplifiers delivering that, you know, in hi-fi. Where you do find Class D amplifiers a lot in hi-fi and also in many other systems is in things like subwoofers. Very common use to see a small Class D amplifier, physically small Class D amplifier, delivering a couple of 100 watts into a subwoofer. Often just single IC based as well, because they're switches, they're not linear devices. So that's kind of where you see them. Anyway, that's the basic principle. One other point I said I'd come back to, which is the feedback. I've shown in here the feedback is obviously picked up after the low pass filter and fed back into the amplifier. So to improve the overall linearity of the system, you would put negative feedback in after the filter, and that would help compensate for it. But actually, unlike an analog or a linear amplifier, which absolutely just won't work without feedback, really, or it just won't work mostly, unless you put an awful lot of effort into designing it. With a Class D amplifier, you don't actually need feedback. You'll get fairly reasonable output. However, the filter will definitely delinearize it and cause sorts of problems. So typically there is some feedback in these amplifiers. So I've shown it there as optional. You can have it with or without. All right. So the next thing to do, I think what we'll do is we'll take this apart now and have a look and see what's in there. Okay, so first thing to notice about this is, you know, if you at first glance, the thing about a Class D amplifier is it looks a lot more like a switch mode power supply than it does like a traditional amplifier. So if you're used to looking at you know, high-powered switch mode power supplies, this is kind of what you would see, and that's no surprise given the architecture of the Class D amplifier. That's exactly how they work. Now, what is quite common in Class D amplifiers is that instead of having a traditional iron core or toroidal transformer or C-core transformer, you have a switch mode power supply, and that's exactly what we've got in this case. So let's just talk. I'm not going to take it apart any further than this. We can kind of make some guesses as to what's under these devices, under these heat sinks. But as you can see, the heat sinks are actually very, very small. There's two of them, and they're both forced air cooled. And rather counterintuitively, I don't believe that's channel 1 and channel 2, and we'll just run through that now and see what we've got. So mains input here, off an IEC connector, straight onto the board here, and this is very traditional mains filtering. Now you'll find that the filtering here is quite important, because all of the high frequency switching of the actual switch mode power supply and all of the high frequency switching here is all filtered out, getting to the outputs. But there's plenty of room for it to come back this way, and obviously from a regulations point of view, you don't want to be putting noise back out into the mains. So, that's quite important. I suspect there's power correction and stuff in here as well, power factor correction in this switch mode. So we've got the mains filtering, a bit more mains filtering here. Well, that may be DC filtering, smoothing caps. Switch mode transformer. So according to the specifications, this will operate anywhere from 95 to 285 volts AC. So it's got a broad range. Obviously, there's no need to select any voltage or anything. The switch mode will operate in that wide range. So the switching devices and the rectifiers are almost certainly under here. It doesn't look like there's any. That could be the switch, I'm not sure, but basically that's a very traditional main switching transformer. Very traditional main switch mode power supply. Nothing sophisticated about it at all. You'll notice the use of a lot of little riser boards in these, and for the most part, that's simply because in these kind of designs, it's more efficient from a space point of view to put these components on riser boards. If you have a look at this one, for example, you'll see there's a lot of surface area there, a lot of small components. These boards can get very big when you've got a lot of large physical components on the board. So almost every time I look at one of these kind of switch mode power supplies, you'll end up with these vertical risers which have got the control boards on there. So I'd say that's I can't quite get in there to see the chips. It's not that important. I think we can guess broadly what's in here. So these obviously the control boards around the switch mode power supply. Under here, I would imagine that you've got the rectifiers, the high speed rectifiers for the output of the switch mode transformer, and that'll almost be certainly generating a plus or minus I don't know, 50, 60, 70 volts, that kind of range, I would imagine. And one of the things that you'll note is that, for something that's actually capable of delivering 550 watts RMS per channel, that's 1100 watts in total, these capacitors are very small. And of course, that's exactly what you would expect in this kind of design, because actually the switch mode runs at a very, very high frequency. So the capacitors don't need to be that big. And that's another advantage of Class D amplifiers, is that actually, the components are, much smaller, certainly capacitors are much smaller because of the higher frequency. The transformers are much smaller. There's a lot less, and much more commonplace technology nowadays where almost everything is a switch mode. So we've got a main switch mode generating a plus or minus supply, and that'll be coming onto these caps here, I'm sure. And then you've got the audio section here. So if we look at these are the two inputs here. Looks like a front end. These amplifiers are NE 5532s, so they're common low noise preamps. That's the input circuitry for the left channel here. That's the input circuitry for the right channel. That's got all the control circuitry on it. So these boards here will be generating that PWM signal. They'll have the comparator on it and the ramp generator and all that kind of stuff. There's also crystal there, which I guess is the source of the clock. And that's obviously common to both of these boards. And then under here will be the 4 switching FETs. Now I'm guessing there's 4 switching FETs. I don't know if I can catch it on camera. There you go. You can see that they're either switching FETs or they're actually an IC, and it actually could be either. They could be a hybrid IC integrated circuit for each channel. And then this is the output filtering. Fairly substantial inductors, lots of ceramic resistors and capacitors here, making up the snubbing output. There's a couple of relays here as well. So this is the output protection, which I suspect is built back in here, and also this will isolate the speaker outputs once you turn the power on and off to stop it clicking or popping. And that's about it. I mean, they are literally as simple as that. There's really nothing complicated about them. They're particularly hard to design. Now, this amplifier costs brand new only £115. So these are actually very, very cheap. So I don't expect this filtering to be particularly high quality, and looking at it, it doesn't look anything special. And I think that's the thing about Class D amplifiers, is that you have to spend an awful lot of money to get something that is going to have output filtering and actually make this reasonably high quality. For PA use, of course, you just don't need high quality PA systems generally. Whether that's be disco, mobile disco, or just vocal PA, or even a large scale PA, you just don't need the level of quality that you would expect in a hi-fi amplifier. So for the most part, Class D amplifiers are every bit as good for the job to be done. Okay, so I think that's not sure there's much else to say about that. One other thing worth mentioning is just like a conventional amplifier, of course, you can run these things in bridge mode. So this amplifier can either be 2 times 550 watts, or it can in fact be 1 times 1,000 watts. That's what they rate it at. So you'll find over here you've got a switch which sets it either to bridge mode or stereo mode. If you switch it in bridge mode, you put the input in one here, connect the speaker, the single output speaker, to this connection here, which is effectively the positive out. Is wired to the positive terminal out on each of these sides. So Class D configuration can also be used as a bridged amplifier if required. Okay, so I hope you found that useful. If you didn't know how a Class D amplifier works, hopefully that gives you some insight and maybe a sense of how it works. Now, if you enjoyed the video, please give it a thumbs up. Thanks very much for watching, and I'll catch you next time.